Welcome to First Experiments in Electronics. Today we're going to explore the non-inverting amplifier. Our objectives are to introduce the op-amp circuit, explore the mathematics briefly, and then present real-world demonstrations using a function generator and oscilloscope. Note that this video builds on the previous video where we explored the inverting amplifier. In fact, if you watch that video, you'll notice that the upper part is unchanged. So this is the inverting with that 100K feedback resistor as RF and this 10K as RIn. To that, we've added two more resistors, and that allows this side here to be the non-inverting. There's a 100K resistor here, that's RF for that particular op-amp, and then a 10K resistor here. Here's the schematic for what you see on the breadboard. We're using an LM358. Part A serves as non-inverting, while Part B serves as an inverting amplifier. Note that the power is applied to pin 8, where we have 5 volts DC, and pin 4, where we have negative 5 volts DC. You'll notice there are some similarities between the inverting and non-inverting. For example, they both have a feedback resistor, which in this case is 100K ohms for both. However, they differ in where the input is applied. In the non-inverting op-amp, the input is applied directly to pin 2, whereas in the inverting, it's applied via this R1. You'll notice that the non-inverting amplifier has this resistor as well, but this time that resistor is tied to ground. So non-inverting, input is applied directly. Inverting, the input is applied via that R1 resistor. You'll recall that the gain for the inverting amplifier was defined as negative RF over Rin, where this was the feedback resistor, RF, and this was Rin. The non-inverting amplifier has a slightly modified equation. The gain is equal to 1 plus RF over, well, we'll call it R3 in this case. Okay. So here it was the ratio of these two resistors, and here it's the ratio of the two resistors plus 1. Given the 100K and the 10K resistor, the gain for the non-inverting was negative 100 over 10, or just negative 10. Note that the negative number indicates a phase shift because the signal is inverting, right? It's shifted 180 degrees. Whereas the gain for our non-inverting amplifier is 1 plus 100 over 10, which gives us a gain of 11. Momentarily, we will demonstrate that this is indeed the case. Perhaps in the future, we can derive this equation, but that's beyond the scope of our First Experiments videos. Now that we know a little something about the non-inverting amplifier, let's go ahead and evaluate its performance using the Digilant Analog Discovery. From the previous video on inverting amplifiers, you'll recall that this device serves as a power supply, providing plus and minus 5 volts. It serves as a waveform generator, and it serves as an oscilloscope. Recall that the LM358 is a dual amplifier. We have the upper side configured as inverting, and the lower side, or the A side, as non-inverting. The inverting or non-inverting function is entirely dependent on how the resistors are connected. Both amplifiers have feedback. That's via this 1K resistor. So pin 7 loops back to pin 6. Likewise, the output on pin 1 loops back to pin 2. Again, that's the feedback mechanism. The input for the inverting is connected via this resistor here to pin 5, pin 6. Whereas that input is connected directly to the pin in the case of the non-inverting amplifier. In this case, that's to pin 3. We are now looking at the user interface for the digital and analog discovery. You can see that there's a power supply section down here, which is currently turned on. The waveform generator, which is set to deliver a 1 kilohertz, 100 millivolt waveform. And then the oscilloscope with 2 channels. Channel 1 is set to 50 millivolts per division. And you can see here in orange that we are indeed producing a 100 millivolt signal. Again, that's peak. The output is set to 500 millivolts per division. And you see that it's slightly higher, which means that our gain is not 10, but something more. Let's see if we can use a voltmeter to automatically do the calculations for us. Remember, channel 1 was the input, channel 2 is the output, and we see the AC RMS is somewhere around 70 millivolts, and the output is about 782 millivolts. If you divide the output by the input, you'll see that the gain is indeed 11, as we calculated earlier. Let me physically switch to the inverting op-amp. We now see the 180-degree phase inversion. And using the voltmeter, we take 712 millivolts divided by 70 millivolts, gives us a gain of 10, as we expected. I'm going to shift back to the non-inverting. And now we can take a look at the frequency response. So if we drop down to 1 hertz, we can see that the output faithfully reproduces the input. And let's see what that looks like at the other extreme. So let's go to 20 kilohertz first. It's a good representation, but you can see it's starting to have a phase shift. 50 kilohertz. It's not looking as good. More phase shift, and we're starting to see that the edges are not quite sinusoidal. That should be much more apparent at, say, 200 kilohertz, and even more so at 200 kilohertz. Again, significant attenuation, and the output is not a faithful reproduction. As we did in the previous video, I'm now going to shift to a different op-amp. So instead of using the LM358, we're going to use the LF412, which is pin compatible. Power the circuit off. And now power it back on with the new op-amp. You can see that this op-amp is able to produce those higher frequencies with ease. At this point, you might ask, why bother with the LM358 if the LF412 is so superior? Well, that's a fair question, but I don't think it's that simple. The fact that both op-amps exist today implies that there must be some design, cost, or performance trade-offs that would make one op-amp preferable for certain situations. Another way of saying that is just because it appears better on this oscilloscope in my lab does not necessarily mean that it's a better op-amp for you and your particular application. These are all topics to explore in future videos. In the meantime, I thank you for watching. Please leave any questions, comments, or concerns in the space below.